Last time, questions or comments for last time?
This what we for this case metric what states that comes only from E3 means E will always
Infinity of mind. I mean,
okay.
clearly. Yeah.
So not like the finite
No, X matrices are defined as transitions between stuff that happens at very early times and stuff that happens at very late times. Okay. Yeah. Any other questions? Was the algebraic part at the end clear? What was not clear enough? Most of it was not clear, most of it was clear. If any of you can formulate any questions, that would be. Or if you can just narrow down to a part that you found quick. Because we just move on and then, I mean that's not good. So either you make a statement that is clear or you try to tell me what was not clear, if that's possible. Anyone else? Did you understand why we were integrating over moduli? Can somebody explain to me why? Can somebody explain to me what the one that we inserted in the part? Okay, so we inserted this one. So product over K D T I D 1 to number moduli. Then maybe delta function of G of alpha beta minus G hat alpha beta, which is a function of T. Gauge transform. Okay, when we integrated over all gauge transformations and we put a Fadipova determinant here. Okay, so the various questions I'm going to ask you about this. This we said was 1. Why couldn't it have been, suppose we hadn't integrated this. So
there's also the delta function of the insertion. I's and goes.
Okay. Yeah. Now, first, please somebody explain to me why. I'm claiming this thing is 1. Why did I have to here integrate over the moduli?
Because there are metric configurations which can't be reached by videos plus well.
Yes. So, in terms of algebra, why would this not have been 1 if I just chosen a particular modulus configuration?
Because there will be values of G alpha beta for the data function of X.
Yes, exactly. So this would be 0 for some G and 1 for other G's. 1 for the G's that would have been on the orbit, 0 for the G's that would not have been on the orbit. So we cannot just insert this inside the path integral and claim the path integral. It's un-Newtonian. Okay? The only way we can insert it inside the path integral, because remember we're inserting something that we're claiming is 1, which includes an integration variable of the path integral. So it's a potentially dangerous thing to do. It's non-dangerous only when what we're inserting is 1. Okay? Now, once we integrate over all moduli and all gauge transformations, we're guaranteed that the delta function clicks once. Okay, because that's the definition of these moduli. Okay? But when this delta function clicks, the result from the path integral is not necessarily 1. The result of this object is not necessarily 1. Just like as we've seen before, which is to say again, delta of x squared minus x naught squared via x, okay, clicks, but doesn't evaluate to 1. Let's say we integrate 0 to infinity. It evaluates to 1 over 2x naught. So, having a delta function and an integral doesn't guarantee that you're going to get 1. It guarantees you're going to get something non-zero. Doesn't matter, you're going to get 1. And this Faddeev-Popov thing here is to take care of this business. To get the measure right. Okay? And tell me why we have these guys.
It's the 0 points of C.
Exactly. The unfixed diffeomorphisms. The unfixed diffeomorphisms that, if we hadn't had these things, what would we have got? Yeah, but just what would this integral have evaluated to?
The volume of Gates transforms that leave G invariant.
Exactly. The volume of the gauge transformations that leave G invariant, and that volume, we'll study that at some point, but could well have been infinity. Okay, it's the infinity that promotes us. Okay, so we needed to completely get a fixed gauge freedom. Okay, so that there are no flat directions over which we're just integrating with no suppression and therefore getting infinity. Okay, we needed the moduli so as to get 1. Okay, once we include this integral over both moduli as well as completely fixed gauge invariance, we've got a nice well-defined thing to insert in central path array. Okay, now can somebody remind me, so I'm writing down the answer again to the S matrix. The answer was, okay, so we have a product over the matter fields, product over the post fields, and then we had product I is equal to 1 to number of moduli B, K, Gi of G hat. Okay? And then we also have a product over the fixed vertex operators, as many as there were conformal Killing vectors. So, J is equal to 1 to number of conformal Killing vectors. We have C for sigma I hat, fixed positions. Hence, okay, I don't think I wrote the square root G yesterday, I just missed that. So I'll write that and you see why it's needed. Sigma I hat, V of sigma I hat. And then we have the product over all the unfixed guys in the remaining vertex operators, where we have D2 sigma square root G hat with product over unfixed. And why did we have the square root G hat? Because square root G hat would have been 1 if G hat should be flat. Just because, the thing that you started with should have been diffeomorphism in there. So it would have been square root G hat times. Right, I just forgot to write the square root G hat stuff, but it's going to be important for consideration. So this is the full formula. Can somebody remind me where we got these C insertions? From the Faddeev-Popov fixing procedure. Where did they come from? Exactly. So what we did was we looked at what these delta functions were in the vicinity of the fixed point. In the vicinity of the fixed point was just the infinitesimal diffeomorphism. So we get the infinitesimal diffeomorphism times the Lagrange multiplier. That generates the delta function. Then to get the Faddeev-Popov determinant, we make everything Grassmannian. Infinitesimal diffeomorphism became the C. Lagrange multiplier became some Grassmannian Lagrange multiplier. An integral over Grassmannian number of e to the power integral d zeta e to the power zeta a. Okay, that was a route to getting these C's for every fixed vertex. Is this clear? Or now? Sorry to like you. Is it clear? Yeah. Where do we get these three DIGs? From the module. Can you explain a little?
The integral over the module also clicks only once, so you expand it.
There also we did the same.
Yeah, we did
So as far as this integral is concerned, you don't care what was gauge and what was moduli. Okay? You're integrating this metric over all moduli and over all gauge transformations. So in the neighborhood of the clique, you have to integrate over infinitesimal changes of moduli as well as infinitesimal gauge transformations. Okay? So in order to know what this delta function evaluates to, what we need to do is to expand the argument of that delta function in the neighborhood of the clique when you perform an infinitesimal gauge transformation and when you perform an infinitesimal change of moduli. And then, so we did that. Well, the stuff from performing the infinitesimal gauge transformation we dealt with last time. Right? That gives us the Korsney-Grad, the BPC. The new term was the stuff that we got by performing the infinitesimal change in moduli. Okay. How does the argument of this guy change? We infinitesimally change the moduli. Clearly by del gk by del g del g by del tk. Okay? By del g by del tk. Now, what did we do? We took that delta function and made it b times tangent metric. So, we made it the bosonic tangent metric, but then to generate the Faddeev-Popov determinant, we changed everything to Grassmannian. Okay? We changed everything to Grassmannian, and so what we got was this factor of exponential of b del I g. Times the infinitesimal change in modulus. The infinitesimal change in modulus, the actual modulus, was a bosonic number. But to generate the Faddeev-Popov determinant, that becomes a fermionic number. Right? So once again we have V del Ig times zeta I. What is it? Eta I. Eta is the fermionic version of the infinitesimal change of modulus. And then once again we use this formula for that eta I. That brings out a factor of this up. Is this clear?
That we root these numerals again.
This inner product includes this
Okay,
thing. The diffeomorphism invariant inner product. So this thing, what does it mean? It means B alpha beta, G alpha alpha prime, and G beta beta prime, del by del I G alpha prime. With square.
Integrating over dt.
What?
Integrating over dt.
Integrating over dt. Yeah, so integrating just over t is just a modulus. There's no root g in t. Okay? Okay, excellent. But I understand the sense of your question. We're going to address this. Okay, the sense of, yeah, okay. So let me just say where Ronald's question was leading. You see, what this is, what we've got, of course, we've got the integral over moduli left.
So the integral over below is at d2 sigma or dt? Later part.
D2 sigma.
Oh, okay. Sorry.
Sorry, that was what you were asking, sir. So we have, of course, the integral over moduli left. Where is the integral over moduli? Where we put it in. It's here. The remaining stuff came from the Faddeev-Popov, but the integral over moduli was there. Is this clear?
When you exponentiate it and then do the Grassmannian integral, so doesn't it just from the density by dt without the dt?
No, because what was the exponential? It was b del g by del k times zeta
Okay.
e to the power this. Then you do the integral over zeta.
So that will
Look on. You understand?
Doesn't it take care of the modulus? Like integral with the modulus?
No, this is the computation of the Faddeev-Popov determinant. You see, we're inserting this tied to the Faddeev-Popov determinant. Then all this stuff with the going to the point where it clicks, changing finite to infinitesimal, just computing the Faddeev-Popov determinant. All that goes into computing this metric. But this stuff has been inserted. And this stuff includes the DDK. Is this clear? Is this clear? Intuitively it should be clear. Because you say, intuitively what were we doing? We were integrating over all metrics. Now we've used diffeomorphism invariant to make it easier for us to integrate diffeomorphism and while invariance to integrate only over some metrics. But we clearly have to integrate over every class of metrics that cannot be connected by diffeomorphism and while invariance. That's what moduli parametrics. Do you see intuitively? Do you understand this? We're doing the integral over the space. Originally, we were doing this integral over the space of all metrics. Then we broke up the space of all metrics into equivalence classes, those that were equivalent to each other under diffeomorphism and while. If we had only one equivalence class, correct. But if we have many equivalence classes, clearly we have to do an integral over the classes. The moduli parameterize those classes.
So what are the diffeomorphisms left for which we have to include this sigma minus?
Let me give you an example. Let's work it out as a sphere. What are the diffeomorphisms left? Well, some of you may think you know the answer. Can somebody tell me what are the diffeomorphisms left for which we have to include this?
So when we do this path integral over C, there are angle C's which automatically satisfy the conformal killing equation. They will never enter this e to the beta alpha, beta grand alpha, C beta. So they are essentially left out.
Exactly. So as you say, the diffeomorphisms are the zero modes. But that's just another way of saying, because what was the differential operator acting on C? It was the change in the metric minus twice part. So they're called conformal killing metrics. So it's those diffeomorphisms that change the metric only up to a Y transformation. Suppose we started with a plane with metric, flat metric. What are those diffeomorphisms?
Radius dependent dilations.
What?
Radius dependent dilations.
Radius dependent dilations. Yeah. What you're saying is probably a subclass of just analytic and anti-analytic diffeomorphisms. Zeta z is an analytic function. Zeta bar z is an anti-analytic function. Take your mind back to the first 2-3 lectures. Remember, we talked about what? We imposed such a gauge condition when we were doing Lycon quantization. And then we asked, what does this not fix? It didn't fix diffeomorphism of sigma plus that were functions only of sigma plus, sigma minus that were functions only of sigma minus. Okay? When we continue to Euclidean space, that's z, which is a function only of z, and z bar function only of z bar. Just analytic diffeomorphisms. And when you say it this way, you might think, well, isn't the space of analytic diffeomorphisms infinite? An infinite number of data expansion. And it sounds like an infinity that's independent of your genus. Okay? But the point is that we're going to integrate over compact Riemann surfaces. So we're going to need these analytic and anti-analytic guys to be regular over the whole space. So any compact Riemann surface, always patchwise, can be made flat. Okay? But with transition functions between different patches. Okay? And we're going to require that the whole thing is regular everywhere. That will limit the number of. So let's take it. Okay, I'll just try it again. Okay. Okay. So, what was the differential operator? The differential operator was, so what we had was C, which was a vector field, CZ. And it had to play the condition del Z bar C Z was equal to 0. Okay? So, what is the most general solution of this equation that is regular at Z equals 0? Well, CZ is equal to sum over M, AM, Z to the power of. And that's got your infinite amount of data. But the point is that this thing goes up at infinity. All of these look like this law. Huh? Which of these are allowed to blow up? Which give you regular behavior? Now, you see the plane is actually a way of representing the sphere. How do you do that? What you do is to take one patch around 0, another patch around infinity, and glue them together by the conformal map Z goes to 1 over Z. By which I mean there are two coordinates that you can use. That there is a conformal transformation that will bring Z equals infinity to 0. What is that conformal transformation? Z goes, an analytic conformal. Z goes to 1 over Z. Okay? So, suppose we do the following. Suppose we work with now, I'm going to call it the W coordinate. You should not confuse this with the W coordinates in the silicon. Maybe I should call it something else. Maybe something else that sounds like a complex number. U. Yeah. Okay. I'm going to call it the U point. U is equal to 1 over Z. Okay. So now suppose I had this kind of behavior. I have C, which is some function of Z. I want to know what vector field it translates to in the U coordinate. Well, that's really easy, right? Because we use the formulas for diffeomorphism. Remember that C under conformal transformations, which is a conformal transformation was product of a diffeomorphism and a wild transformation. Remember, C was wild invariant. C with an upper index was wild invariant. So under these wild transformations, these things that we used to glue, these patches, it transforms exactly like a vector transform. Because it doesn't transform, it transforms only under the diffeomorphism. This is very easy. Okay? So, how does a vector transform under the diffeomorphism? Well, Cz is equal to del Z by del W CW. Okay? Excellent. So we have Cz is equal to minus 1 by Z was 1 by U, so 1 by U squared Cu, or Cu is equal to equal to minus 1 by Z squared Cz. Is equal to U squared Cz minus. Okay? Now see, suppose we had Cz. Okay? This is a regular vector field on the full sphere, provided it's regular at the two dangerous points. It's obviously regular actually. There are two dangerous points, right? Z equals 0, Z equals infinity. But that's the same, Z equals 0 and U equals 0. So provided this vector field is regular both at Z equals 0 and at U equals 0. Okay? It's regular. But the only way we can see whether it's regular at U equals 0 is by transforming the U coordinate. Because infinity is not a point in Z space. But 0 is a point. Okay? So, now let's look at this guy. this guy is u squared times cz. Now, this fellow blows up. So suppose we transform the cz into this formula just by substituting z is equal to 1 over u. This is u squared, so cu is equal to minus u squared times am by u to the power m. Which of these give allowed behaviors? Anything with m larger than 2 is not enough. Okay? This will blow up unless we truncate m into 2. So what is the set of regular conformal Killing vectors on the sphere? It is simply Cz is equal to A plus Bz plus A1 plus A0 plus A1z plus A2z. Is this clear? Okay? You see from this analysis how it depends on the topology. A sphere is a product of two disks glued. That's what we do. A torus is a more complicated object. A genus 2 surface is a more complicated object. Okay? You also see intuitively that as you go higher and higher in genus, there are more potentially problematic points. It has to be problem. It has to be regular in each disk. So you'll have fewer and fewer solutions. Okay? So that's why on the sphere you have 3 analytic pairs. Okay? On the torus, till now you have 1. It's very simple actually. It's just a constant. Let me tell you the torus. Suppose you got a torus like this. Okay, just identify. All of us intuitively know what a torus is. Right? You identify this side, this side, this side. Okay? Now, you can ask, what are the, and you just use flat coordinates on this torus. Okay, so it has to be analytic, has to be a regular zero, so it has a power series expansion. But it has to respect the periodicity. Which terms with the power series expansion represent the respect the periodicity of this thing? It's basically the constant.
Why not the even?
What?
Even though
Because you have to, when you go here, you have to come back to yourself. This z square won't do it, right? It will have reached 1. Okay? So very similar, I'm saying it crudely. You know, mathematicians would put together many patches to get a torus. But you know what I mean, right? You just get the periodicity and you got it right. Okay? So the torus is only 1. Okay? Every higher genus surface turns out to have 0. Since we started this little exercise, let's work out the number of moduli also on this way. How would we work out the number of moduli? Does anyone have any suggestions? What equation do the moduli obey? It says bar b is equal to 0. Same equation. Same equation than C. You might think same solution than C. Not right. Why not right? Exactly. The moduli transform differently under the normal transform. How do they transform? Like a 2z index tensor. Okay? So the first part of our analysis is exactly the same. We have b is equal to sum over m, bm z to the power n. Those are the regular moduli of the plane. Okay? But the second part of our analysis, this thing that gave us this u square, what will it now become? du 1 over u. Because that was an upper index, this is 2 lower indices. So you get 1 over u to the 4 times bm by um. Which of these is regular at u equals 0? Some m equals 0 to infinity. Which of these is regular? None of them is. So there are no moduli. Okay, what about the torus, by the way? On the torus must there be one modulus for the same reason. Now the constant is well is bigger. Just one case. So we've got this B field. Okay? In a basic equation, del bar B is equal to 0. Solutions to this equation are regular z equals 0. A sum m is equal to 0 to infinity Cm z to bar. I want to know how many of these solutions are regular at z equals infinity. Okay? So to do that, what I do is to remember that B was actually secretly BZZ. So BZZ is the same thing as del U by del Z squared BUU. But what is del U by del Z squared? Del U by del Z is 1 over Z squared, minus 1 over Z squared. So del U by del Z the whole thing squared is 1 over Z to the 4 BUU. Correct? And therefore, I want to solve it the other way. I want BUU in terms of BZZ. I get BUU is equal to Z to the 4, same thing as 1 over U to the BZZ. Now I substitute what Z BZZ was claimed to be. It is equal to 1 over U to the 4. Sum m is equal to 0 to infinity Cm by U to the power m. So the term with 0 is like 1 over U to the 4. The term with 1 is like 1 over U to the 5. The term with 2 is like 1 over U to the 6. None of them are regular cubical 0. Okay? So there are no moduli in the of the sphere. Why are the moduli in the torus, by the way? You see, you can always. A torus is a space with identifications. These two identifications. And by a diffeomorphism and a Weyl transformation, you can always make the metric flat. But at the cost of screwing the identifications. Okay? So the modulus of the torus is simply the vector, the one vector in the complex plane that tells you how you have to identify it. So torus can be thought of as the set of points as the fundamental domain of a lattice identification. Okay? So by choice of convention, we can always take one set of lattice points to lie on the x-axis. The remaining set of lattice points are generated by a second independent vector. Let's call it the complex number tau. Okay? So the flat metric with complex identification. So this I will take to be 2 pi. It doesn't matter what I choose it to be because by scale transformations I can always set it to be any number. So the flat metric with this identification, this to 2 pi and this to tau. Each of these gives me a torus. Okay? And one can show, as we will when we study the torus in more detail, that these different things cannot be identified and cannot be brought to each other. Cannot be Weyl and diffeomorphism related to each other. They're all the same. In fact, we will compute when we study the torus. We will compute this dgk by dt to get right major moduli space of the torus. We do this thoroughly. Okay? So the one modulus, the one complex modulus on the torus is the choice of this tau. Okay? And the one complex diffeomorphism is just shifts along the cycles of the torus. You've got this torus, you put an origin somewhere. Just move, translate along the circle, or translate along the other side. These are the two diffeomorphisms of the torus. This is the modulus of the torus. I said two. I earlier said one. I now say two because I'm moving between one complex and two real. Okay? Higher unit surface is a more complicated to visualize. Okay? And we'll talk about them a little bit as we go. Is this clear?
The condition that we use to write these results is simply that the vector field be regular around origin and infinity.
The vector will be regular everywhere.
Everywhere, right. But that means, why is this looks like a very weak condition, and I don't get why is this sufficient to say that?
Because it will have to be both regular as well as analytic. You see, CZ was an analytic vector. See, you're familiar with the fact, right, that any function, that any analytic function that is bounded at infinity is a constant. So the fact that something is both analytic as well as reasonably behaved at infinity is very restrictive. You know more, right? You know that any analytic function that grows no faster than the polynomial z to the power m at infinity is necessarily a polynomial. So it's the analyticity plus the boundedness that makes it so restrictive. Was this your question?
Yes, and just to add to this, like we still after doing this, it is not the conformal killing vectors that we are. It's just a property that we used to, in a sense, like we have not used conformal invariance anywhere. I mean, there's nothing that says that this CZ is anywhere related to the conformal killing vector or anything.
No, it is a conformal killing vector because it obeys the conformal killing equation. Conformal killing equation is del z bar of c is equal to 0. Now that you might say is the same as the conformal, the modular equation. Because that's also del z bar of b is equal to 0. However, this equation has to be obeyed in the appropriate local coordinate patches in every patch. Okay? And these things have to transform over. So what we're doing is finding solutions to the conformal killing vector equation. That gives the idea. Plus appropriate boundedness. Meaning, just that is well defined everywhere. But from the point of view of the plane, that turns into a growth state. Do you see? Not 100% satisfied. If there's any way you can verbalize, articulate your insights.
I just wanted to see how this is related to the conformal killing method that we usually see.
You're saying that. Suppose you are okay. You know, I think that what you are interested in is it. What you are interested in, perhaps, is suppose I take the round metric of the sphere, and then I try to solve the conformal killing vector equation. Then, okay, how would I get these solutions?
Yeah.
Okay, now this is the point. The point is that we don't, that you can do that by, for instance, expanding spherical harmonics. Okay? And of course you get the same answer, but that's an unnecessarily complicated way to think. Because patch by patch, the round metric of the sphere is while equivalent to flat space. It's just that while transformation blows up at one point. Are you familiar with the fact that the round metric of the sphere is while equivalent to flat space? It has a name, it's called stereographic relationship. That is for that. Suppose I have this two-dimensional sphere. Okay. And I make the map that I set up the North Pole and I project points onto the plane. Okay? Now, the space I get by doing this projection is while equivalent to the space with the round metric of the sphere. And you can figure out the while transformation factor. Okay? Now, because the conformal killing vector equation doesn't care about the while transformation, because it's confined. Okay? You can as well solve the problem on the plane. Okay? But there's a problem. The problem is that it doesn't care about the while transformation, but if the while transformation goes to infinity, you should start worrying. At this point, it goes to infinity. Clearly, right? One point is there. Going from here to here is a small distance, going big goes up to a huge distance. Okay? So why don't we do the following? Why don't we think of a second stereographic projection, which is this one. Okay? Both of these have their problems. Okay? But then, problems at different points. So what we can do is solve the problem here. Solve the problem here and ensure that the solutions patch together where they overlap. That's exactly what I did. I solved the problem in a Z space. Then I solved the problem in U space. Then I ensured that the two things were the same at every finite zero, every non-zero finite zero. Same under conformal transformations, which was just diffeomorphisms in this case, because these things were wide invariant. Is this clear? Okay? And then I ensured regularity in the good coordinate system for each match. That's basically what I did. So I'm solving the problem you want to solve, but much more easily than you would, by using a trick. Okay? But, if you feel uncomfortable about this, why don't you as an exercise try the following? It's not a difficult exercise. Take the two-sphere, we're all familiar with the two-sphere with the round metric. Expand the most general vector field on the two-sphere. Most general vector field can be expanded as, yes, what spherical harmonics? And vector spherical harmonics and scalar spherical harmonics. Two dimensions vector spherical harmonics are particularly easy. We're wasting time. Anyway, vector spherical harmonics are particularly easy to buy. You see, because suppose you've got some scalar spherical. One way to get a vector, get a vector field is to take a derivative of this scalar spherical harmonic. Another way to get a vector field is to act in this derivative with alpha beta. Okay? That gives you vector spherical harmonics. Vector spherical harmonics in two dimensions are just epsilon times derivative of the scalar spherical harmonics. Okay? So since you know all about scalar spherical harmonics, you know all about vector spherical harmonics. Okay? Then write down the conformal Killing vector equation. Okay? And solve. The fact that we know the answer here, because these polynomials tell you the angular momenta. The fact that we've got, okay, just solve. Okay, spin two estimates here. Hey, you just try it. You get the same thing. Okay. But I just did it with a trick because it's easy. Okay, good question. Other questions about it?
Some sort of mismatch between CZ and CU. It should be symmetric, but when you A0 and A2 exchange meaning other than.
Okay. Let's.
I'm not sure if the question, but.
No, it's a good question. Let's try that. The question is, if we worked in U coordinates, you should also get constant plus U squared. Yeah. If you worked in Z coordinates, you should also get constant plus Z squared. But if you just put Z equals 1 over U, you're not getting that. And what's the answer?
No, the answer is of course the U squared sitting outside.
Yes.
But the A0 and A2 are exchanging. The A2 becomes constant coefficient, A0 becomes Z squared for U.
Yeah, that's how it is.
Is that the exchange between K mu's and P mu's in the equation and
K mu's? Maybe there's a way to take it. But yeah, it's just that the guy that has the largest Z power will have the smallest U power. It's the inverse. I mean, maybe there's something more to say, but it's fine. The set has to map to the set. It's not. Okay. Good. Other questions, comments? Excellent. So now we're all experts on moduli and conformal Killing vectors of the sphere. We have intuition for this stuff. So great. Let's get back to our formula. Okay, actually, since we've started talking so much about these things, let me try to derive this formula that the number of conformal Killing vectors minus number of moduli minus number of conformal Killing vectors is 3 minus 3. Okay? So the mathematician would do this in different language, when we use physics. Okay? So, it's an interesting exercise. We start with the so-called ghost current, if you want to call it C. We start with the so-called ghost current of the BC system. Okay? Now, in our analysis of conformal field theory, I should have spent some time on discussing this current. I'll make amends now. Okay? So, firstly, as we discussed before, this ghost current has, I call the G ghost. J ghost has the following property. Times B is times C, Z, W, Z. What do we have? Z. Z and W is equal to 1 over Z minus W. Whereas I'm keeping the G, the ghost. It's always Z and V of W. Is equal to minus 1 over times C. Right? Times V of W. This tells us that the charge that you build by integrating the ghost current, that the C field has charge 1 under the charge that you build by integrating the ghost current, and the B field has charge minus 1 under the charge that you build by integrating the ghost current. What is the connection between this and the charge? Can somebody say one or two more sentences about what I just said? Why does this statement mean that C has charge 1 under the ghost current?
You look at the integral over a spatial slice of J, and that will give you an operator in the Hilbert space, and that just will be the eigenvalue of the neutrals.
Exactly. So, as we've seen by contour tricks, the pole in the OP is what happens when you take, when you compute the commutator of the charge with that current. So this is the statement that the commutator of the charge with this current with C is equal to C, which is the statement that C has charge 1. Okay? This is the statement that B has charge minus 1. Okay? So this is a current under which C has charge 1 and B has charge minus 1. It's a current that the charge counts number of C insertions, C oscillators minus C excitations minus number of B excitations. It's a charge that we used heavily in proving the no-ghost theorem. Okay? Now I want to investigate this charge a little. This current. So what I want to do is to understand what happens to this current under what the OP of this current is with the stress tensor, with the BC stress tensor. And for that I'm going to need somebody's help in remembering what the BC stress tensor is. So del BC minus with a lambda something. If somebody can look up their notes, otherwise I'll look up it. Well, this is right including signs. Del BC minus lambda del BC. Okay, excellent. Del BC minus lambda del BC. Perfect. Okay. So now I want to know what is this T. I want to know what is T of Z J of W. Okay. So that's not too hard. Let's do it. So that's del BC. So I'm going to do it term by term. First I'll do this with J of W and then the lambda. So del BC times J of W, which was C. All this I've said, and C, B, and W. Okay? So what can we get? We can get the contraction between C and B. So that contraction will give us minus del B of Z C of W. And this was a contraction of C with B, so it gave us 1 over Z minus 1. Is this clear? Because this is just a simple pole, we can replace Z. Okay, that's one term. Second term we can get is with contracting this del B with this C. But by the way, I got this minus because I took this C through the C. So now I should get del B with C. Once again, I have to take del B through C, so I get a minus. What will be left behind is C of Z and B of W. And what will I get then? I'll get derivative, Z derivative of 1 over Z minus W, which is another minus Z minus W squared. Okay, so this term was this. Next, I want this term. So this term is just derivative with respect to Z of BC on the course capital.
Would there be one more term which is fully contracted?
Oh yeah, fine. Thank you. Plus 1. Thank you. So the term that's fully contracted, as you correctly point out, this term is minus 1 over Z by W. And this term is, that's just 1 minus sign, minus 1 by Z. So it's plus 1 by Z minus W. Thank you.
So should we also Taylor expand C?
Should we Taylor expand C? We should. We should. I'm going to leave it now, combine with the other things later. Yes. So okay, good. So if we Taylor expanded the C, we would get C of W, B of W plus del C. Okay, let's write that out. Let's do it. So what we get is, from the first term we get 1 over Z minus W the whole thing cubed. Then plus C of W, B of W, Z minus W the whole thing square, plus del C B minus del BC over Z minus W. Now, this term is more simply written as, how have we written that? We've written the ghost current as CB. So I'll write it as CB. So that is simply equal to 1 over Z minus W the whole thing cubed plus J over Z minus W the whole thing squared plus del J over Z minus W. Right, where I've used that del DC is same as del DC is same as C del with a minus. Okay, so far so good. I've got the terms independent of lambda. Now let me do the terms with the lambda. Okay, so the terms with the lambda minus lambda times d by dz of BC of Z with CB of W. Okay, so that's minus lambda del Z of, well, we can have C contracting with B. So that's B of Z, C of W over Z minus W plus C of Z, B of W. That will be reduced.
First term is very minus. Oh, you're taking minus.
No, the minus out, I think every term had a minus sign and I cancel the minus. Is this accurate? We would see C with B both given we have a minus sign. Okay, the terms differ only because one has a ZW, the other has a. Oh, and they differ in order. Let's see, this one was BC, this was CB. Yeah. Well, full contraction, and the full contraction. Thank you. And the full contractions were C with B, which is 1 over Z minus W, and B with C, which is another 1 over Z minus W, minus sign. So minus sign, so plus 1 by z minus w squared. Okay, all happy? Okay, now we have to do the differentiate.
There's one more minus sign in the relationship I may be wrong.
Between this and this?
Yeah, because you're contracting.
Let's see. First guy I contracted this with this. I had to take the C through here, so I got a minus. This and what was left over was BC. The second guy I took this and contracted here. I got a minus sign because I took B through C. So both of them had minus sign, but lambda came with a minus sign. So I thought, I think it's okay. Shruti is not looking at it.
So between the first term and the second term, is there a minus sign?
That's
No, I'll go to the second term and the third term.
between this. Okay, let's say to contract C with B, I had to take C through C and a minus sign. To contract B with C now, there's no further minus because this is already been taken through. So only one minus sign. Okay, that's all. Everyone happy? Okay. So now we take this z derivative. See, what can we do? So we get plus lambda. Now z derivative can act here, so there is b. And once we take the derivative, because this is a simple pole, we just substitute that. So del bc, these are w. Plus del c b at w. Okay, by z minus w. That's one term. Plus lambda, then we take the derivative here. Okay, so that becomes minus lambda bz cw plus c of z b of w by z minus w whole thing squared. Okay? Plus minus lambda minus 2 lambda 1 over z minus w the whole thing. Okay, now we're just going to group terms together, do some Taylor expansions, and we're through. So what about the 1 over z minus w whole thing cubed? 1 minus 2 lambda by z minus w whole thing cubed. No argument about that. Okay? Now what about the squares? Here we had j by z minus w the whole thing squared. Do we get a contribution to the 1 over z minus w the whole thing squared from this stuff? No. Because we set z equals w, this is just 0. Okay? So plus j by z minus w the whole thing squared. Okay? And do we get contribution to del j? Well, let's see. For del j, we need to Taylor expand this. Okay? So here we will get del bc plus del cb. But it appears with a minus sign. It's exactly what we have from here. Okay? So these two cancel each other. So plus del j by z minus. So dj equal. A lot of this we knew had to work. You see, this part, works for any local current. As long as you've got a valid stress tensor. This part works for any local current that has a particular dimension. In this case, the dimension of J was 1, that's why we got 1. Okay. These two terms we knew had to be lambda independent. They were just universal. The only thing that could depend on lambda was this. Okay. So what does this tell us? Is J a primary operator? Only at lambda equals half. See, lambda equals half is the point where the BC system is actually free fermions. We haven't discussed that. We will. Okay. So only at lambda equals half. Lambda not equals half, in particular, lambda equals 2. It's not a primary operator. Now, primary, you see, J is a count. And these two transformations here were just the okay. So Tj tells you how J transforms under an infinitesimal conformal transformation.
Why do we have a cubic circuit?
Why do we? Is that like
in a sense, if you have a JT, then you have your minus n.
we would, but T and J are not the same one. JT is different from TJ. No, I mean, what I mean is that, sorry, I say that you see there's no contradiction. Suppose you had JJ and you got 1 over ZQ, what Z minus WQ, there would be a contradiction. Because you got the same operator. So just changing the sign does not change the answer. But there will be a contradiction. It's here. The point is that the thing you may be asking is, do we get 1 over Z minus W the whole thing cube, or do we get 1 over W minus Z the whole thing cube? And the answer is we get 1 over Z minus W cube, where Z is the coordinate in T, and W is the coordinate in J. No confusion. Symmetry, it's always powerful when you've got two identical things. It's always basically contentless. They're not identical. Because they're different.
Dimensional is universals.
Exactly. Good point. If you had something proportional identity, it had to be Q. Okay? Now, some point in our lectures, we very carefully try to understand how these things translated to transformation properties under infinitesimal conformal transformations. And the point was that the conformal transformation was beta of Z times T of Z. And we just saw what the pole in this current was by looking at the zeta times T. So the pole in this current will give us del Z squared zeta into 1 minus 2 lambda. Because you have to expand this twice. Plus del Z zeta J. Okay? Plus zeta del J. This was the change in J under an infinitesimal conformal transformation. You recognize this part as the change because you moved because of the translation of the coordinate. Do you remember we worked this out very, very carefully? We wrote down the tensor transformation properties of a tensor with many lower z and many lower z bar indices. Okay. You can look at that part again. This part was just because of the change in the coordinate. Okay, because you wrote z as equal to z of z prime. Okay, and the tail expansion rate. This part was because of the vector index. These two came from the fact, from the transformations. You see, conformal transformation is a diffeomorphism compounded with the Y transformation. These two gave you the diffeomorphism transformation properties. This is new. What does it tell us? It tells us that J is not Y invariant. So what we need to do is to figure out how J transforms into vector. Okay? Now, I'm going to work this out up to signs and factors and leave the filling out to you. Okay? Because it will be hard work to figure out whether the signs in particular, which is where I'm doing active passive. That's what it's happening. Okay? We did it very carefully that time. Okay, the formula was written down here on the board. Lower indices. We got every factors played. It would be 15 minutes a day to get those factors played. Okay, yeah, but this term here, firstly, if we do an infinitesimal diffeomorphism, what is the compensating Weyl transformation? If I do a diffeomorphism, sigma goes to sigma plus theta, that changes the metric. What was the compensating Weyl transformation? Good. Del dot zeta. Exactly. Is this clear? So the conformal transformation. So let's do it. Suppose we do sigma z goes to z plus zeta, z bar goes to z bar plus zeta. Okay, then dz bar goes to what? Okay, dz bar goes to dz bar into 1 plus del zeta plus del bar zeta plus quadratic, but we're not keeping that in the del. Okay, so this is the Weyl transformation factor, the compensating Weyl transformation. Now you have to think hard about whether it's this over the minus sign. I'll leave on that. Okay, so the Weyl factor corresponding to a conformal transformation was del zeta plus del bar zeta. Okay, this thing transforms like this. Can you think of a formula that depends only on the Weyl factor that reduces to this? The formula is, let's call this delta W. Exactly. 1 minus 2 lambda times del z of delta W. Okay? So, delta Jz, 1 minus lambda del z of delta W minus 2 lambda. Delta Jz bar, similarly, holomorphic part of this calculation, is 1 minus 2 lambda del z bar of delta W. So delta J mu is 1 minus 2 lambda del mu of delta W. So we've got a nice covariant formula. Okay, basically the thing that tells us that we're on the right track is that there's a lower Z index here as well. Okay, so how does J transform under Weyl transformations? The transformation of J under Weyl transformations is delta J mu is equal to 1 minus 2 lambda del mu. Is this clear? As you will see, this discussion is very similar to the discussion that we had when we computed trace of the stress tensor in terms of the curvature. It's a discussion that's very similar. Okay. Now the next thing I'm going to ask is, what is del dot J? How does del dot J transform under Weyl transformation? Because J transforms like this, del dot J transforms like del of this. And therefore, delta of del dot J under Weyl transformation is equal to 1 minus 2 lambda del square of delta W. What does this tell us? It tells us that it's impossible that del dot J is 0. Because if it was 0, independent of Weyl factor, then its transformation under Weyl transformation would be 0. But del dot J is not 0, its transformation under Weyl transformation is proportional to identity. There's no operator there. Okay? So So we want some expression that has the right dimension. So dimension 2 should be a scalar, should be proportional to identity, and should have this wild transformation property. Can you give me a candidate thing it could be proportional to? Scalar curvature. Scalar curvature is a scalar. Scalar curvature is dimension 2. Scalar curvature under wild transformation transforms with the del square delta W, at least around flat space, around the delta W. See? Okay? Now what you have to do is to look up with what factor the scalar curvature transforms. Make sure you're using the same dimension for this delta W there as the favorite book to look up. And so on. Okay, so you're getting there. So it follows that del dot J will be equal to some number 1 minus 2 lambda times R times maybe half minus 1 minus 2. Some such a number. Then you look up which is to find what the number is. Okay, let's see if I can find this. It's here. 2 lambda minus 1. So the number is less simple than I thought it would be. 4. Okay, so I'll leave it to you as an exercise to fill out the signs and factors in this derivation. Is this okay? Okay, so we've got del dot J is 1 minus 2 lambda by 4 times scalar curvature. Wonderful. Okay. Now, the fact that del dot J is not 0 on a manifold of arbitrary curvature is sort of interesting. But it may seem pretty... and the question we're going to ask is, what are the implications for computing path integrals of BC systems on surfaces of higher genus, of surfaces of arbitrary genus? Now, why is that an implication at all? There's an implication for the following reason. You see, there is this beautiful theorem in mathematics the integral square root G times R over any two-dimensional Riemann surface is a topological invariant. You can easily check this for yourself. For instance, that the variation of this expression in 2 dimensions locally is by a total derivative. Something that you can easily check for yourself. Okay? And because it's it's like a total derivative, it only cares about global stuff. Okay? And this topological invariant evaluates to 2 minus 2g, where g is the genus. Okay? I think certainly 0 G equals 0. I may have to put an extra 2 somewhere. If I can find it. Yeah, I think it's right. Yeah, let me just find it. I can give you the text. This is called Riemann rock theory. Let's look at some things. Ah, 152. minus 2g. Right. So just one. I think that's right. Okay, so you get this 2 minus 2g. Just 4 pi. Okay, I'm sorry. I may need to add a number as we move along. Let me I can't find it. It's written somewhere in the pages. Okay, let's some number. Some number. Maybe it's 1 over 4.
2 pi pi.
Well,
2 pi into 2 minus 2.
2 pi into 2 pi is 2. Okay, excellent. 2 pi into 2 minus 2. Okay, excellent. Good. So,
the fact that the divergence of the current level vanishes is to be related to the fact that it's not a prime, it can make whether it's a primary or not. Like if it's a primary, then it vanishes. If it's not, then it doesn't matter. Why?
It's exactly what you said. You see, if it's not primary, then it transforms under Wien transformation. Therefore, its divergence transforms under Wien transformation. So you can reverse. The zero doesn't transform. Right? And it's basic. That was our derivation. We computed the transformation of del dot j under Wien transformation, and then found out the right coefficient so as to look at that. Okay. See, now what's the basic point? The basic point is that because of this, the integral of this equation, okay? Because of this, the integral of this equation over any genus G Riemann surface is not zero. But it is something that is entirely determined by the genus of the Riemann surface. Well, you see, so let's take this equation and integrate it. The integral of the left hand side is the integral of the right hand side. But the integral of the right hand side is simply 2 minus 2g times some number times this coefficient. Okay? So we get integral del dot j square root g is equal to 1 minus 2 lambda times 4 times 2 pi times 2 minus 2g. Is this clear? Now, what is the significance of this? What is the significance of this? Let's think of what the integral of del dot j over all of space-time is. For a moment, think of just flat space. Okay, suppose we had some space-time and we had some time slice. What's del dot j? It is the production of charge. So the integral of del dot j gives you j in the future minus j in the past. So it tells you by how much charge conservation is violated. Okay? We can make this more formal as follows. Let us remember our derivation of the Noether theorem. Okay? Let us remember our derivation of the Noether theorem. Okay? Where does J appear in the game? Suppose we had some transformation, we had some symmetric transformation, delta phi is equal to epsilon. So now I'm talking abstractly for the next 5 minutes. Doesn't matter what the term is. Okay? Epsilon and x for phi. Some infinitesimal transformation. Then what we did was make this epsilon a function of x. We knew that the action was in action and measure were invariant under this change of variables when epsilon was a constant. Okay? And therefore we got that the whole change was del mu epsilon times some j mu. Okay? So we got that the path integral was the same as the path integral with this insertion. Okay? And therefore we got the equation that del dot j was equal to 0. Okay? Now, how are we going to get an equation that says del dot j is not 0? Okay? That says del dot j is not 0 but something. The way we get an equation that says that del dot j is not 0 but something is if we had that something times epsilon in the variation of action discussion. Inside the path. When we did this change of variables. Okay? The action plus measure will change with not just the del epsilon times j. Because if it did, we would just get the equation del dot j is equal to 0 up to the contact terms of whatever it is. Okay? But if we want to get the equation del dot j is equal to something, we would get that if that something appeared in the change of variables here. Is this clear? Okay. Excellent. So, now, actually, when we look, we had d phi e to the power minus s. Okay, the change in this with the change of variables was this plus 1 by 2 pi, again leaving minus signs, del mu epsilon j. Okay, so to get the right thing, we had here del dot j was okay. So suppose that we want the equation del dot j is equal to alpha. We need a plus a minus alpha epsilon to appear with the same one. Is this clear? Okay. Now, in the case that we had a symmetry, we could deduce that in the case that we had a symmetry, we could deduce that the number of, if you want some transition amplitudes, okay, that the net charge of all the insertions under that symmetry have to vanish. How do we deduce that? Well, we just make this change of variables. Okay? We make it with constant epsilon. Make the change of variables, make it with constant epsilon. So the change of variables does not change the action, because this part is not there, that part is not there. But the change of variables changes the acts on the insertions. And the action on the insertion is just the net charge of all the insertions. Okay, this sounds very abstract. Let me say in the BC system. Suppose I've got some path integral which is dB BC, C sigma 1, C sigma 2. But the number of these is NC. And similarly, we've got some B insertions. The number of these is N. Okay? Now I do what symmetry transformation would give me the host current? Rephasing of C by e to the power I alpha and rephasing of B by e to the power minus I alpha. Okay? That's the finite form of the transformation. I might as well use the finite formula. Okay? So how do the insertions change? They change by e to the power I alpha into NC minus NB. If under the change of variables, the action just did not change, we would get the formula that transition amplitude, by transition amplitude I just mean this path integral of these insertions, is equal to the same transition amplitude times this phase. And therefore this transition amplitude is 0 unless NB is NC. I'm saying something that you all know. Right? That if you've got a symmetry, then you have to have as many plus as minus insertions. The only charge neutral insertions give you something non-zero. This you know, right? Right? In operator language, if you've got A1, A2, A3, vacuum is annihilated by some charge, you say 0 is equal to Q acting on all of this, because it's 0 because the charge annihilates the vacuum from the left. And then you take it through. Each time you take it through, you become a factor of the charge of A1, the charge of A2, the charge of A3. And then you get 0 by acting on the right. So this whole amplitude is equal to sum of charges times amplitude. So the amplitude is 0 unless sum of charges. Yeah, same thing. This is the path integral. This is clear? Okay. Now, we're in a situation where the current is not conserved. So this term is not there because we're doing constant transformation. Then we epsilon 0. But this term continues to be there. So now what do we find? We find that apart from this phasing, we get a new factor. What was this new factor? The new factor was just this alpha integrated over all of space. But alpha integrated over all of space was just del dot J integrated over all of space because alpha was delta. Okay? And so was this distance. Okay? We had a 1 over 2 pi here that cancels rho x 2 pi. It's 4 pi right. Okay? So we had a 1 over 2 pi here that cancels half of rho x 4 pi. Okay? And so we get number, so you see we get number of C minus number of B insertions inside the path integral has to be equal to 1 minus 2 lambda by 2 into 2 minus 2. Okay, I'm going to put a plus minus for safety. Okay, in fact I know how it goes because I know that if lambda equals 2, it's the number of B insertions that grows as the genus grows. So in fact this is number of A over it's B minus. So do you see what we've concluded? We've concluded that if we do the BC path integral, on a surface of genus G, we will get 0. Okay? Unless the number of B insertions minus the number of C insertions is something quite simple. Now, let us focus on the particular case of interest to us, namely lambda equals 2. So lambda equals 2, this is minus 3. So this is equal to 3 into G minus 1. The first good thing is that it's an integer. Without, if Ron had kept it 2 pi, it would not have been an integer. It would not have been an integer. Okay? The second thing is, what does it evaluate to at g equals 0? Minus 3. How many conformal killing vectors did we have? 3. Okay? What does it evaluate to at g equals 1? 0. In that case, we have as many conformal killing vectors as moduli. Okay. Now, what is the connection between this number and the number of conformal killing vectors? You see, this was an anomaly way. This was the anomaly way of understanding when the path integral was not zero. But from
shouldn't that be number of B0 and number of C0?
B0 is what?
The 0 mode.
It will relate. At about through in the derivation, just number of B insertions minus number of C insertions. But when related to the number of zeros.
It is not related to this effect becoming a person and moduli unless the B0 and C0.
I agree. We're coming to that. Okay. Yeah. What mechanism within the path integral, okay, can force an integral to be zero? See, this is the analysis from symmetries and anomalies. Okay? But now suppose we're just doing a path integral, we've got some insertions. What mechanism can force B and C? What mechanism can force the path integral to be zero? Okay? There is a very simple mechanism in the path integral involving fermions. It's zero modes, integrals over unsaturated zero modes. That can force a path integral to be zero. Okay? So, if the action has some number of B0 modes and some number of C0 modes, okay? Then you will get zero unless you put enough insertions to absorb the B0 modes and the C0 modes. Okay? So suppose you've got some number of B0 modes, some number of C0 modes. You put as many insertions as you needed to absorb the B0 modes. As many insertions as you needed to absorb the C0 modes. Then you're going to get something non-zero. Okay? So you get something non-zero when the number of B's is the number of B0 modes. And the number of C's is the number of C0 modes. Okay? So this thing which tells you that in general you get something non-zero only when number of B's minus number of C's is something, is also counting the number of B0 modes minus number of C0 modes, because the mechanism for getting zero is not being able to saturate the zero modes. So this tells us that the number of NB0 minus number of NC0 is equal to 3 into 9. And so we conclude that the number of moduli minus the number of conformal killing vectors. Okay? Number of moduli minus number of conformal killing vectors is 3 into 3 minus 1. In explicit agreement with our explicit countings for G equals 0. Moreover, the only way you get a zero mode of P dagger is if P dagger on that object is 0 by taking norm. And the only way you get a zero mode of P dagger P is if P on that object is 0 by taking norm. So, we've got these two square operators.
Can you take down the
Yes. So, you see, suppose we take the operator P dagger. Okay, so what have we got? We've got the operator P dagger P, and we've got the operator P dagger P, and we've got the operator P dagger. There are two statements. One, this operator and same non-zeros. Eigenvalues with equal multiplicity. It's a one-to-one map between the non-zero eigenvalues of these two operators. Okay, the map is simply generated by acting with P or acting with P. Okay, 2 0 modes of P dagger P are those states that have P on C. Okay? That this implies this is obvious. Because if PMC is 0, then P dagger PMC is 0. So that this implies this is also obvious because just take the norm. Suppose P dagger PMC is 0, take the norm with C. That tells you PC with PC is 0. And therefore, PC must be 0. Okay? And similar statement, 0 modes of PP dagger. Same thing as P dagger B. Okay? So, now when I'm doing my path integral, what was my path integral? My path integral was okay, and maybe I'm taking the time to just relate the normalizations. Okay, so suppose I start P dagger P on nu I on Ci is equal to nu I Ci, and I choose my basis to be orthogonal, so that Ci Cj is equal to 0. Is equal to delta. Distinct modes are, of course, orthogonal as usual, but also I've chosen this thing to be unit normalized. And I choose my modes of the other guy. P dagger and Bi is equal to nu I Bi, such that Bi Bj is equal to delta Bj. Okay? So if I choose both these to be true, then I want to know exactly what the relationship between Ci and Bi is. Now, we know that Pi Ci is proportional to Bi.
What is P?
Sorry, P Ci is proportional to Bi. Because we know that PCI is an eigenvector with eigenvalue I. Okay? And now, in order to compute the proportionality factor, I just take the norm. Okay? So the norm of this side, so let's say this is equal to alpha times Pi. Okay? The norm of this side is just P dagger P Ci but P dagger P on Ci was nu I. Ci with Ci was 1. So this side is nu I. Okay? So this is equal to alpha squared times the norm of alpha Bi is alpha squared. So what this tells us is that this alpha is square root. Okay? In a similar way, we would find that P dagger Pi is equal to square root nu I Ci, and all the nu i's were positive, so square root nu I is a real number, and by acting with this twice, you see that you recover the eigenvalue equation for series. P dagger P on Ci is equal to nu I times Ci. Right? This way. I can P dagger here and then use this. Okay, so everything's nice. Okay, so these are our conventions. Now let's see how we can rewrite the coast action.
Why were you doing for it?
What? Because they were eigenvalues of positive definite operators.
Alright.
P dagger. Okay? So let's see how we can rewrite the coast action. Okay? So the coast action here is, of course, so what do? We take, maybe it's not a good idea. Maybe it's not a good idea. I've been calling these CIs, but I may think I should use CIs with coefficients of the expansion. I need another name. Let me call. Okay, I'm switching names. Now, what I've been calling CIs, I'm going to call it gamma i's. What I've been calling DIs, I'm going to call it D. Okay? So now the general C field can be expanded as C of sigma is equal to sum over I Ci, gamma I or sigma. Just an expansion of a field in complete set of functions. And B of sigma can be expanded as sum over I, bi, beta I of sigma. Okay? And the i's in these two things run over the same values except for 0 modes. So let's take the 0 modes out. Plus sum over m, this is the number of moduli. Right? So k is equal to 1 to m, cm times gamma m of sigma. That's the 0 mode wave function. That's the coefficient of the 0 mode. Okay? And plus, so this was the number conforming to ck. K is equal to 1 to m, bm, beta m. I'll call it beta gamma 0 beta c. Well, we just found the a basis of functions. We're expanding C in a basis of functions with arbitrary coefficients. The basis of functions we're using are eigenfunctions of the operator P operator.
The second part, 0 modes. There is one function that you. What is how many modes? K equal.
All the various 0 modes.
Okay.
Was this the confusing thing that this was called? This should have been K. Was that what was confusing? Now, if we take this expansion and plug it back in, take this expansion and plug it back in into our expression for the ghost action, which was BPC. Okay, what happens with P when we act on gamma I? Okay, when we act with P on gamma I, let's, in order not to have these square roots, let me call the eigenvalue gamma I square. Will that be good? Okay, let me call the eigenvalues delta I square. Okay, I'll keep. Okay, so we've got P with PC. So you plug in this expansion. P on gamma I is beta I with respect to this. Okay, so you see that what we get is just sum over I, Ci, Bi, Ci square root. Of course, the 0 modes don't appear because P kills the 0 modes and P dagger kills the 0 modes. That's why the 0 modes. Okay, so we've got an expression in terms of the coefficients. Now, just look at the structure here. In the expansion here, these are anti-commuting numbers, but these are just functions. Okay. So we've got an expression which is quadratic in these anti-commuting numbers. So the path integral now is dBdC is just integral dBi product dCi over all non-zero. Okay, times product I is equal to 1 to moduli dB0 I. Product I is equal to 1 to conformity of vectors dC0 I. So path integral over functions can always be turned into a path integral over the coefficients of an expansion function in a orthogonal basis. That's what we've done. So this path integral over the ghost fields is this object. The action was this object here. Okay? Now we also had insertions. But the insertions were exactly as many C insertions as C0 modes. And exactly as many B insertions as B0 modes. So in the insertions, imagine putting the expression of the field. Putting this expression of the field. do you see that because there are exactly as many zero modes as insertions, it's only the zero mode part of the insertion that will contribute to the path integral. Let's take an example. Suppose there were two C zero modes, and you have two C insertions. You get C sigma 1, C of sigma 2. Okay? Now, each of these is this expression here. It's a quadratic expression in all the modes of C. There are objects which are quadratic in the non-zero modes of C. There are objects that have a non-zero mode and a zero mode, and there are objects that have two zero modes. But fermionic path integrals have the property that DC0, now there are two zero modes, DC01, DC02. It's only non-zero if the expression that's being integrated has a C01 and a C02. There's no zero mode from the action. So you're not getting any contribution from there. So this contribution has to come entirely from the insertions. So anything that it does not take the maximum number of zero modes from the insertions, we just integrate to 0. So the insertion, from the insertions we only pick up the part that involves zero modes. Nothing that involves a non-zero mode from the insertion survives at all. Is this clear?
But this action has this non-zero modes.
Action has the non-zero modes. So that's why you don't get 0 from the non-zero modes. But the insertions, so the path integral of the non-zero modes can be done once and for all, because it doesn't care about the insertions. The part in the insertions that involves non-zero modes does not contribute to the path integral. Okay? So, the path integral over the non-zero modes is simply square root of determinant of p dag of p prime, by which I mean determinant ignoring zero modes.
This determinant is coming from this part, like just the action.
Now we got this action, and then we do the integral over the non-zero modes. We do this integral. Okay, that just gives you one factor of square root gamma I for each I. Is this clear? Say, suppose you're doing d alpha, d beta, e to the power alpha beta square root gamma I. It's quadratic. I mean, this is cross multiplication. It's fine. The first order term contributes. You have d alpha, d beta, alpha beta square root gamma I into the square root gamma I. Okay? But square root gamma I, product of square root gamma I over all non-zero guys, is exactly the determinant of p dagger p, or the determinant of p dagger, where you explicitly instruct the determinant to run only over the non-zero modes. That's the prime of that expression. The whole thing is sort of primed. Okay? So the whole role in life of the non-zero modes of the BC growth system is just to produce this one determinant. It's not an unimportant determinant, it's there. But it doesn't care about the details, it doesn't care about what you're inserting. Okay? Everything really interesting has to do with the zero modes. The zero mode integral is still there. Now let's explicitly evaluate the zero mode. Okay? So what we have to do is now the zero mode integral. So let's do the C part. The zero mode integral is we've got dC01, dC02, dC03, and the insertions were what? We only get the zero mode part. So the first insertion was C01 gamma 01 of sigma 1 plus C02 gamma 02 of sigma 2 of sigma 1 times the same thing with sigma 2 times the same thing with sigma 3. Now if you've got a path integral, if you've got an integral over fermions like this of such an expression, do you know what it evaluates to? Let's do 2 cross 2. Determinant. Yeah, it's clear if you do 2 cross 2, for instance. The guy which is C01 times C01 gives you nothing. C01 times C02 gives you the So what you're going to get is the determinant of gamma 0 I sigma j. Okay, how is this a determinant? Determinant of what? Well, there are as many I indices, that's the number of C01s, as there are j indices, that's the number of fixed vertex operators. Because you needed that completely fixed equation. So it's a square matrix in I and j, determinant in this space, is what you get from the C sequence.
Number of I is correspond number of chain vectors.
Number of conformal Killing vectors, yes. And number of j indices was the number of fixed vertex operators, which was the number of conformal Killing vectors. Okay? Similarly with the B0 modes, what will you get? You get determinant of del G by del Tk B0 I j. Same argument. Same number of I indices as j indices, right? Because the number of I indices came from the number of moduli, the number of j indices came from the number of moduli. Okay? Once again, you're doing an integral over fermions, you get the same symmetric things, you get this determinant. Okay? So now we've done the integral over the all the ghost modes. The zero mode integral of the ghost modes gives you this determinant. The zero mode of the C ghosts gives you this determinant. The zero mode integral of the B ghosts gives you this determinant. The integral of the non-zero modes of the ghost sector gives you a rather trivial determinant. Okay? These are the 2 really important parts in the path. So now, by doing this, we've reduced this expression to a path integral only over the Mann sector. Okay? Now, it will sometimes, when we actually compute scattering amplitudes, prove useful to do it this way. Sometimes it will not. But it's useful for formal problems. Sometimes it's more useful just to do the path integrals including the ghosts. It's sometimes easy. Okay? But for formal applications, it's useful to do that. So we've got one expression for the string S matrix, which does not involve ghosts. Okay? Any questions or comments on this? Okay, now in the last 5 minutes of this class, there are various formal properties of the string S matrix that I wanted to discuss. I'm not sure we'll get through them all, but let's start seeing. And okay, I'll mention them all. Okay, I'll mention them all. Okay, let's see what I do. Firstly, what was the role in life of the B-ghost insertions? The role in life of the B-ghost insertions was to give this extra factor. So the integral over moduli, product over I dpi, okay, gets this quantity, determinant of V0I dg by dt. Now, without such a factor, the expression we had written wouldn't have made sense. Why not? Because you can ask, what are the TIs? TIs are some parameters that parameterize the space of inequivalent metrics. But I haven't told you what parameters. So if you choose one set of parameters, I choose another set of parameters, in going between the integral of my set and your set, there will be a Jacobian. So you could have asked, whose preferred parameters would give me the right answer? Because it can't be both, because that's a Jacobian. But now look at this. Because of the chain rule of partial differentiation, under variable change of t, this will change like dti by dti tilde. So the determinant becomes a determinant product of two matrices. And a determinant of a product of two matrices is product of determinants. And that second determinant is precisely the inverse Jacobian. That cancels the change in measure. Does anyone want to see the details of this argument? Is this clear? So if I move to a new integration measure, here I will pick up the Jacobian. T goes to T tilde, which is roughly dt by d tilde. It's the matrix of, it's the determinant of the matrix dt by dt. But if I go to the new, if I write this in terms of t tilde, again, the point is here I have a t upstairs, here I have a t downstairs, so it's about
G prime also, G tilde also depends on that.
what?
G tilde, that's the picture on this.
The metric on moduli space? Yes. G tilde? Yes, G tilde depends on t.
So when you change the...
I'm just doing a variable change. Now I've got a space of metrics on the moduli space, and I'm just doing a reparameterization on the coordinates that label that space. Okay? The point is that this transforms like square root g. Like the square root of the metric on moduli space. Okay? This together is an invariant measure on moduli space. So without this factor, the answer would not have been right or wrong, it would have been nonsensical. Okay? So, firstly, the role in life of this stuff is A, it absorbs away the zero, it came from absorbing away the 0 volts. But once you've done that, it gives you the right measure. It fixes the measure for integration over moduli. That was what B would do. Great.
Any question energy and say beta naught I go by to T J is some Gij for the moduli space.
Except that this. Maybe there may be some sense in this. Yeah, in fact, that's probably true. It's probably true. Yeah, that's probably true. Yeah, this together, for instance, in the torus, this will give you just the d2 tau by m tau. Okay, so that's probably true. Okay. But there's no square root factor. So you can only get square root of. So it's like some sort of square. It's like a farm. Something like that. Something like that. You get the right measure. Okay. Excellent. Now, another thing that I want to show. Very good. Okay. Another thing that I want to show is that that my final answer is independent of. If I take my standard metric, which is this G tilde, and I do a Y transformation, that is independent of that Y transformation. We've been working in some reference metric. If I Y transform that reference metric, it shouldn't change my answer. Okay. Now, various factors here depend on the Y factor, so they have to cancel. What about these? The thing is, let me say it and then we say it. Okay. See, what about square root g? Square root g depends on the Y factor, obviously. But what about v? The vertex operators. Do they depend on the Y factor?
Because they're point-wise actually.
Because the point-wise. You see, the question is, these v's, how do they transform under conformal transformations? These were under diffeomorphisms, they were scalars. But they had weight 1, 1. So if you had a field that transformed, whose conformal transformation properties were entirely diffeomorphism transformation properties and were scalars, there would be 0, 1. And the only transformation of scalar under diffeomorphism is the derivative term. There's no weight term. But all of these are 1, 1. Which tells you how they transform under wild transformations.
Is your 1, diminishing force?
Sorry? Holomorphic and anti-holomorphic dimension. You remember our discussion of this DRST quantization, right? A vertex operator over 1, 1 matter operators times C. You remember this was to satisfy the physical state condition. Okay? So the fact that they're 1, 1 tells us exactly how they transform under wild transformations. Because they're scalars, so we know how they transform under diffeomorphisms. But they're 1, 1, so we know how they transform under conformal transformations. So from that we can deduce how they transform under wild transformations. I'll show you next class in more detail. But they transform in exactly the right way to cancel the transformation of square root g. So square root g times v are wild invariant insertions, and that's what's being inserted. So the insertions are nice and wild invariant. Okay? Now the only thing that is C is explicitly wild invariant. The path integral measure was wild invariant, that we checked in great detail. Okay? The only thing that's not wild invariant is this. Okay? The only thing that's not wild invariant is the insertion B L K of G. Now let's look at this expression. In what way does it transform under wild? This is B alpha beta, G alpha alpha prime, G beta beta prime, del K of G alpha prime beta prime. And times square root G. Integrated. So under a constant scaling, this transforms like G, this transforms like G, these two transform like G inverse. So under constant scaling, it's 0. But a wild transformation is not just a constant scaling. Okay, if you transform G goes to e to the power 2w times G, the w can depend on derivative. So the part where this derivative, okay, the part where the derivative, the point is that the wild factor can be chosen in a moduli way, in a way that varies with moduli. There's no canonical way of choosing the wild factor for different moduli. Okay, so there will be a term where this derivative hits the e to the power 2w. But that term is proportional as this contracting with b, which gives you the trace of b, which was 0. Okay? So this term, no matter how closely to what standard you hold it, is wild. Okay? So everything is wild. I'm basically giving you the argument. I can say it more slowly next time if there's need. Yeah, the last thing, this in 2 minutes it will be over. The last, actually no, this BRST. I just say, let me say, what about our diffeomorphism? You see, it's a bit strange. Diffeomorphisms are a bit strange because of two things. Because A, there is no canonical way to relate the diffeomorphisms in metrics with two different moduli. And B, we broke in diffeomorphism invariance by putting insertions at specific points. Okay? So there are two sources of diffeomorphism non-invariance. Okay? Those two sources of diffeomorphism non-invariance have to do with differentiating the diffeomorphism, infinitesimal diffeomorphism vector with respect to modulus, and the the insertions of and the explicit diffeomorphism vector we get when we move C. Okay? That's a beautiful thing. The part of the term that you get because of the change in diffeomorphism vector when you move the modulus is basically, that's left with it. You see, that's just B del kg. Now, how does G change? G changes by P of the diffeomorphism field. So, B del K of P of zeta. Okay? The part that's dangerous is this del K of zeta. That you choose a diffeomorphism vector that is that cares about where you are. But this is just zero by equation of motion because you move this P dagger B is zero. However, equation of motion inside path integral is true only up to contact terms. Okay? Contact terms occur at insertions of C. Okay? And the contact term in the Ward identity that allows you to use this equation of motion actually is exactly the small diffeomorphism change of C. So I'm saying that the two problems, the fact that there are two things that change under diffeomorphisms, cancel each other. Okay? By the Schwinger identity, which is the equation of motion obtained by differentiating the path integral with respect to C. I'll show this to you what it is. Okay? So it's a very beautiful thing that this thing doesn't look diffeomorphism in there because you've broken good things of parent points. But it is because of the Schwinger equation. The last thing I have to show you is BRST invariance, that the vertex operators that you used can be replaced by any other vertex operator in the same BRST class. I'll show that to you next class. We'll miss that. Okay.